Today we're going to talk about the chain rule extension to multivariables as well as its use in implicit differentiation. In a single variable chain rule, we have an outer function f which is applied in an inner function x, and that is evaluated at time t. And so you have this composition function. And the chain rule then says the derivative of the composition is the derivative of f at x of t times the derivative of x of t. When you go to the multivariable case, there are two things that could happen. So you have this outer function g of x and y, and then what do x and y depend upon? So if we were looking at a curve, x and y would depend on a single variable. So we would have f of xt, yt, but if it were a surface, then it would depend on two variables, s and t, say. So you'd have f of x, st, y of s and t as well. And so we come up with two different chain rules depending on whether we're depending on one or two independent variables, t and st respectively. So in particular, we'll let g, x, y be a function of two variables and f, x, y, z be a function of three variables. Obviously, these things have to be differentiable in their variables, probably continuously differentiable. So we use this gradient notation already, that the gradient of g, x, y is equal to the partial derivative of g at xy times I, which is a unit vector pointing in the positive x-axis, and gy plus the partial derivative in y of xy times this vector j pointing into the positive y-axis direction, being times j, which is a unit vector pointing in the positive y direction. Or similarly, in the three variable function f, the gradient has the partial derivative in x times the unit vector pointing the x axis plus the partial derivative in y times the unit vector pointing in the positive y axis plus the derivative in z times the unit vector k pointing in the positive z direction. And these gradient notations will help us to keep our chain rules compact. Now, there are two different chain rules that arise when you're dealing with multivariable functions. Remember, curves basically have one independent variable, whereas surfaces have two. So we'll look first at curves. For an example question about what we're going to try to do here, we could consider how fast is a particle in space with position ut, being the vector position xt, yt, zt, approach the origin? Well, the answer is the negative of the derivative of how the size of that position changes. So the size of that position actually is how fast it's going away from the origin. So how fast it would approach the origin would be the negative of that. So there is a quick way to solve for this, and we do so by letting f of t be minus the size, which is the Euclidean distance from 0 of u of t, and using this partial derivative chain rule with one independent variable. That is the partial derivative chain rule for curves. Suppose that r is equal to f, x, y, z, and x is equal to x of t, y is equal to y of t, and z is equal to z of t. So they themselves are functions of one independent variable. Then one could ask, well, what's the overall change in r with respect to t? dr dt is then the partial derivative of f in x times the derivative of x in t plus the partial derivative of f in y times the derivative in t plus the partial derivative of f in z times this regular derivative of x in t. And now we will see that our gradient notation we introduced is useful, because we can rewrite this compactly as the gradient of f times the derivative of u in time. And for this rule, it's important to see that there only is one independent variable, and that is t. Another way of writing this is in the full derivative notation, where we think of the total derivative of f of x of t, y of t, z of t in t. So the derivative df dt. And we write that as a gradient of f at u of t dot product with the derivative of this vector u at t. So as an example, we can ask how fast is the particle at position u of t, which is x of t, y of t, z of t, which is t squared, t cubed. Approach the origin. Well, in this case, our function is the distance from the origin. So fx, y, z is the square root of x squared plus y squared plus z squared. So its partial derivative in x is just simply x over the square root of x squared plus y squared plus z squared. And the gradient then is the vector x, y, z over f of x, y, z. Also, we can take the derivatives of x and y and z and determine that that vector is 1, 2t, 3t squared. We can also look at the distance, which is the square root of xt squared plus yt squared plus zt squared. And then simple algebra shows that that's t times the square root of 1 plus t squared plus t to the fourth. Now we can substitute all this into the formula for df dt, with f being equal to the Euclidean distance of u, and find that minus du minus the derivative of the size of u dt is equal to minus the vector x of t, y of t, z of t over this size, square root of xt squared plus yt squared plus zt squared, times the velocities of the individual components, x prime t, yt prime, zt prime, and then this works out to 1 plus 2t squared plus 3t to the fourth over the square root of 1 plus t squared plus t to the fourth. And you could ask, well, is this really approaching the origin? So we can go backwards in a sense and go to the two-dimensional curve chain rule. So we still have just one independent variable t, but now g is just a continuously differentiable function of two variables x, y around t, while g is continuously differentiable around x of t, y of t. Then if we let r be g of x of t, y of t, then the derivative of r satisfies dr dt. The full derivative is the partial derivative of g in x times the derivative of x with respect to t, plus the partial derivative in g with respect to y times the derivative of y with respect to t. And we can rewrite this in the compact gradient notation again as the gradient of g at u of t dot product with u prime of t. Here u is this vector function for position, x of t, y of t, and r is just g of x, y. And so how do we prove this? Well, the proof basically follows from multiple applications of the mean value theorem. So we just write again the increment of r in time, so rt plus h minus r of t, and that by its definition is g of xt plus h yt plus h minus g of x of t y of t. But then we add and subtract, like we did above, this term g of x of t plus y of t plus h. And then we use the mean value theorem to express that first two terms is the partial derivative in x of g at some x h t y t plus h times the increment in x. And we do the same thing for the terms in y, the change in y, to get the partial derivative of g at x of t y h of t for some yh times the increment y of t plus h minus y of t. So here x h of t is something between x of t and x of t plus h, and y is something between y of t and y of t plus h. Now we divide this equation by h and then let h go to 0 and use limit laws to observe that these increments divided by h approach the derivative by the definition of the derivative. We can move on to the partial derivative chain rule for surfaces, wherein we have two independent variables, t and s, say. So x now is x of t and s, and y now is y of t and s. And if we have a function of three variables, then z is also z of t of s. And we either have our same old functions of three variables f, x, y, z, or two variables g, x, y, and we assume they're continuously differentiable. So in the two independent variable case, t and s, the partial derivative chain rules that we developed above become the partial derivative chain rule for two independent variables. Suppose we set r is equal to f, x, y, and z being functions of these two independent variables. Then now it's a partial derivative in t, di r, di t, because now r depends ultimately on both t and s. So there's just not one variable, hence we switch the notation to partial derivative. So the partial derivative in r with respect to t is the partial derivative in f with respect to x times the partial derivative in x with respect to t, plus the partial derivative with respect to y times the partial derivative of y with respect to t, plus the partial derivative of f with respect to z times the partial derivative of z with respect to t. And that is taking s to be a constant. And we have a similar formula if we take t to be constant. Partial of r with respect to s is the partial of f with respect to x times the partial of x with respect to s, plus the partial of f with respect to y times the partial of y with respect to s, plus the partial of f with respect to z times the partial of z with respect to s. In gradient notation, things become a lot easier. So if we let uts now be the vector of x ts, y ts, z ts, then we can express these two chain rules just above in more compact notation. So we have the partial of f uts, that is just like the partial derivative of r with respect to t above, but now we can simply express this as the gradient of f at uts, scalar product with the derivative with respect to t of uts. And we have the exactly same formula in s where we think of t as constant. This is the case where we have two variables and we have a surface over space. We have also a planar case where u of t and s is still the vector of xts and yts, but there is no z anymore. And we have a very similar formula. It looks identical in the gradient notation. For example, di by di t of g uts is equal to the gradient of g at uts, scalar product with the partial in t of uts. So this is completely analogous to the formula for the derivative in r with respect to t above, except for there'd be no z term. We can move on and discuss the use of chain rule to solve the mystery of implicit differentiation. So suppose that we have a constant c and we had a setting where capital F of x, y is equal to c. So this could be an implicit description of some type of curve, because setting a function of two variables equal to a constant more or less makes one dependent upon the other, although the dependency can switch in different locations on the plane. Or alternatively, we had a three variable function, capital G of x, y, and z, setting it equal to a constant, which often describes a surface. And you wanted to know dy by dx, say. Note equations like fxy is equal to a constant or gxyz is equal to a constant generally reduce the independent variables by 1. In the first case, we can write y is equal to fx where the curve is not vertical. Then by the chain rule we would get di f di x dx by dx plus di f di y dy dx is equal to 0, because we differentiate both sides of the equation fxy is equal to a constant with respect to x. The derivative of the constant is 0. And now we also know that dx dx is equal to 1, So solving, we get the implicit differentiation formula dy dx is equal to minus the partial of capital F in x over the partial of f in y. Example, a planet revolves around a sun according to the ellipse. X squared over 9 plus y squared over 10 is equal to 10. So then we have that f of xy is equal to x squared over 9 plus y squared over 10, and then we've set it to the constant c is equal to 10. And so the implicit formula implies, and dy dx is equal to minus the partial derivative in x over the partial derivative in y. The partial derivative in x is just 2x over 9, and the partial derivative in y is just 2y over 10. And if you simplify that, you get 20x over 18y, and you multiply it by that minus 1, and then you can divide 2 from the top and the bottom. And this makes sense provided y is not equal to 0, which means that there is such an f so that y is equal to f of x. As we know already from high school, if the slope of the curve becomes infinite, there is no function. Otherwise there is. In the surface case, where you have two independent variables, we need to know when does the function have an inverse. Well, there's a nice answer to this, and it's through what's called the implicit function theorem. Unfortunately, it's a little beyond the scope of this course, and it tells us when we could write z is equal to gxy from the condition capital Gxyz is equal to c. And when this is true, and so we would just assume it's true in our problems, then by the chain rule on capital G of xy and little gxy, we get the following formula. The partial of capital G with respect to x times the partial of x with respect to x plus the partial of g with respect to z times the partial of z with respect to x is equal to 0. And so noting that the partial of x with respect to x is just 1, and solving, we get the implicit differentiation formula that the partial of z with respect to x is equal to minus the partial of f with respect to x over the partial of f with respect to z. The main difference now is we use partials, since z can be written as a function of two variables, x and y. Of course, there would be a similar formula for the partial of z with respect to y, or for that matter, the partials of y with respect to either x or z, and x with respect to either y or z. Thank you.